Okay, we're gonna get started on the first of 6 lightning talks. We're really excited to have Sophie, who's a rising second year PhD student in computer science at Cornell, advised by Nikhil Garg and John Kleinberg. So much.
Awesome. So I'm really excited to be presenting this work that I've been doing with Nikhil and Subbulakshmi on user and item fairness in recommendations. So the way the talk is going to go, I'm first going to introduce the problem that we're solving. I'm then going to introduce our theoretical model and a framework we use to solve the optimization problem. Then I'm going to show some theoretical results that we get from this framework, and finally end with empirical results, like looking at these theoretical results in empirical settings. So recommendation algorithms are a massive part of many online platforms. We see in platforms such as Amazon and eBay, products being recommended to consumers. In social media, we see content being recommended to viewers. And our guiding focus is going to be the setting of academic paper recommendation, where papers are recommended to readers. And so these recommendations affect users' utilities. And they also affect the utilities of item producers. In the simplest case, a producer is going to be very sad if their item is never recommended. And the utilities of users and items may be misaligned with each other. And so in recommendation, a variety of papers and algorithms exist to ensure fairness to items. These involve trading off platform performance with item fairness objectives. And in order to do that, they have to make the platform perform slightly worse for some users in order to give items higher utility. And in particular, this can reduce the utility of some users more than others. So in a recent paper by Greenwood, they developed an algorithm that uses different users having weaker preferences to ensure item fairness to those to the items. And while this is like appropriate in some settings, this shows that it is easier to ensure item fairness when you kind of differentially decrease different users' utilities. And so this motivates the study of user fairness. And so there's been a variety of really wonderful work developing algorithms to balance user fairness, item fairness, and overall platform objectives. And also some recent work understanding the relationship between these two objectives. So recently, Wang and Yakim's show that there is a fundamental tension between user and item fairness objectives, which we kind of saw suggested in the last slide. And recently, Kleinberg and Meister characterized the worst case cost to users of item fairness constraints. And so we're going to kind of build upon this work and look at how these two different types of fairness trade off, and in particular, how this depends on the setting in which recommendation is being performed. So we see here, there is kind of trade-off curves between that we could generate between item fairness and user fairness. This is from some simulations we ran. Don't worry about what those were, but the idea is you can look at kind of the trade-off you get between item fairness and user fairness. And this purple curve, for example, the trade-off is very sharp. In order to guarantee a certain amount of item fairness, you're going to have to decrease user fairness by quite a bit. Versus in the yellow curve up there, you're seeing very low trade-offs between these two things. And what could these things be? So our first theoretical result that we're going to show is that user preference diversity reduces the price of item fairness on user fairness. And the second result we look at is the price of misestimation. And in particular, when users' preferences are misestimated, this hurts different users differently, imposes a user fairness cost. How does adding item fairness constraints increase that cost? Does it increase it, etc.? So to go on with the model, this is our model of user and item utilities. We have n items and n users, and user I and item j get utility wij when item j is recommended to user I. So w could represent a purchase probability or click-through rate. It's generally some utility. The platform is choosing recommendation policies. So for each user I, it chooses a distribution, a distribution row I over the different items, and recommends an item according to that distribution. So this induces a expected utility for each user paper combination. And a user's utility is going to be the expected utility over all items that it could be recommended. And an item's utility is going to be the expected utility over all of the users. So fundamentally, there's kind of a difference in what items want from a recommender and what users want from a recommender, even though they both share this utility matrix W. How do we define item and user fairness? So first, we take item and user utilities and we normalize them by the maximum they possibly could get. This is to avoid having some users who just absolutely hate everything and caring about their preferences too much. And similarly for items. Then for fairness, we define it as the minimum user's utility and minimum items utility respectively. So kind of Rawlsian definition of fairness. And so we formulate this optimization problem to try to capture the trade-off between user and item fairness. So gamma here is a parameter that's going to capture kind of the fraction of the optimal item fairness. Does this work? Yes, wonderful. Okay, so gamma is capturing the fraction of the optimal item fairness you might want to get. And then we're going to impose this constraint, obtain this fraction at least. And then under that constraint, what is the optimal user fairness that you can get? And so for different levels of gamma, you get different decreases in user utility or user fairness due to that item fairness constraint. We can kind of describe the trade-off happening there. So this is a concave max-min optimization problem. So it's easy to solve numerically using, for example, CDXPy or Gurobi, but it's difficult to find a closed form for the solution algebraically. And our goal is to understand how this optimal user fairness depends on the setting W. So we do want an algebraic solution. So yes.
Is the reason why you chose multiplicative rather than additive? Or do you think things would substantially change if you did additive?
I think it doesn't. So you're talking about gamma?
Yeah, sorry.
I think it doesn't substantially change things. Normalization, right? Maybe like the way the curves look. Sorry,
That
might look a bit different.
Nothing.
To tackle this, in particular, we're going to be caring about the price of fairness and price of misestimation. And so the price of fairness is going to be the decrease in user fairness caused by imposing. Yes, caused by imposing item fairness constraint. And the price of misestimation is going to be the decrease in user fairness here caused by misestimating W as W hat. And in particular, we're really going to care about this case when gamma equals 1. And so we really need to solve this optimization problem in the specific case when gamma equals 1. And so to do that, we first observe that finding the optimal item for a solution, we can reduce it to a linear program. And also, if we are able to, if we know we're in a setting where there's only a few unique different user preferences, the solutions to the linear program are sparse. So this is going to allow us to find a closed form solution to that convex program earlier. And this is what we're going to use to generate our theoretical results. So I'm going to move on from the technical stuff. If you have questions about the details of that, you can find me after. So what are the theoretical results that we find? So remember, these are kind of the qualitative high-level results. We find that user preference diversity reduces that price of fairness. And we find that item fairness can exacerbate, actually arbitrarily, the price of misestimation on user fairness. And so to make that concrete, the specific setting that we look at the price of fairness in is kind of a simplified setting of utility where an alpha fraction of the users have utilities V1 to Vn for each item. And the remaining users have utilities Vn to V1. And this alpha parameter essentially captures how diverse the population is. So if alpha is approximately 1/2, there's kind of a lot of diversity, a lot of heterogeneity in the population. But if alpha is approximately 0, most of the population is dominated by that second type of user. And obviously this is kind of a very simplified setting. And in the second part of the talk, we're going to look at what if we use real user utilities? Do we still see this theoretical result? So yeah, we're interested in the price of fairness, which you'll call is the decrease in user fairness caused by imposing maximal item fairness constraints. And we get the result that as alpha increases, the price of fairness decreases as long as alpha is less than 1/2. And intuitively, what this is saying, that as the population gets more diverse, the price of fairness decreases. So diverse preferences lead to free fairness. For our misestimation result, we consider a similar setting in which a fraction 1 minus beta of the population, the platform has no data on, and so doesn't know what their utilities are. And so the platform is going to estimate their utilities as the average of other people's utilities. That's kind of the best guess. Does this for each item. And the price of misestimation is, you can imagine if we had the, if we had the, the user fairness using the true matrix and the user fairness using this estimated matrix, what's the difference in user fairness? Because we estimated. And our theoretical result is that if we, the price of misestimation can be arbitrarily worse if we have item fairness constraints. So when there's no item fairness constraints in this setting that we consider, the price of misestimation is always going to be less than 1/2, but we can, as long as beta, the fraction, is not too small, always find, and beta is the proportion of correctly estimated users, importantly. We can always find some preferences, some possible utility matrix such that the price of misestimation is arbitrarily high. So the question is, does this happen in practice? And in order to analyze this, we developed a recommendation system trained on archive data that recommends papers to readers. So we train language model embeddings on archive abstracts. This allows us to obtain user item similarity scores with which we estimate the utilities and perform a recommendation. And we take these utility values and we plug them into our theoretical results, and we're able to look at that trade-off in that optimization problem we saw earlier. And we evaluate our recommender using the citation data, and you can see that it performs very well. I can interpret that plot for you after if you have questions. And so what do we see empirically in terms of our theorems? So for the first theorem, we look at two different ways of drawing a population, a subpopulation population. So first, our samples are just randomly selected from the population uniformly. And then we also cluster the users and uniformly select a cluster at random. And when we select the clustered users, you can see that the trade-off between item fairness and user fairness is steeper than when we select the users randomly. And of course, the clustered users are going to be a more homogeneous population because they're clustered by their embedding. However, for the price of misestimation, we don't see such a serious result. So before we saw this kind of very steep trade-off between, or we saw this like arbitrary increase in the price of misestimation after adding item fairness. So what that would represent is these two curves kind of splitting apart as you increase gamma. But in fact, we don't see this effect because the price of misestimation without item fairness is already super, super low. So what are some future directions of this work? So one thing we're super interested in is looking at other definitions of fairness and seeing how these theoretical results extend and how we can use the theoretical framework to potentially extend to other definitions of fairness or to develop additional theoretical results such as the two I presented here. And we're also interested in if we add overall platform utility constraints, how that interacts with the trade-off between user and item fairness, because this is something that people do in the real world. They don't just care about user fairness and item fairness, they also care about having an all-around good platform. So my other interests are in behavioral modeling. I'm interested in human algorithm collaboration. And so I'm really interested in looking at kind of behavioral aspects of recommendation, looking at user choice in recommendation, and understanding how we can build better recommenders to work with users. So in conclusion, we study user item fairness trade-offs in recommendation and how they depend on the setting. We noticed that user preference diversity can decrease the price of fairness, and we noticed this both theoretically and in empirical data. And we also noticed that while in theory, item fairness can arbitrarily increase the price of misestimation, in practice, this does not really impact things. Thank you for listening.
We have time for a couple of questions before the next talk.
Am I right that your recommendation probabilities have to be IID for each user? So you can't say like, I'm gonna show one person item A, one person item B, I've got 50-50, which one is which?
Yes, we're assuming.
Right, does that drive any of the results? 'Cause I would feel like things would be more fair if you could say, I'm gonna show items depending on what I've shown in the past.
So my first reaction is that like a lot of things we're doing here are linear, and so linearity of expectation might make this not an issue. I think, yeah, you mentioned in the past, and we're not really considering a time, but that's also interesting, I think. So yeah, I don't have an answer off the top of my head, except my kind of assumption is because of the linearity, it probably is not a big. Hi.
In the like misestimation, you like had the model where the algorithm like guesses the average probabilities for the. Is that like the most reasonable thing you could do? Like, do you know that nothing could do better than that in this like price of misestimation?
I think, I think it probably depends on the setting. There are other reasonable things you could do. I think, for example, like randomly choosing something. But I think it is a very reasonable thing to do if you have absolutely no information to just assume they have preferences.